In this video, we will discuss about classification of systems. Systems are broadly classified into two types, continuous and discrete. Just as signals were classified into two types, continuous and discrete, systems are also classified into continuous and discrete. So first one, continuous time systems. So what is a continuous time system? A continuous time system is the one which takes continuous time signal as an input and produces a continuous time signal as output. So both the input as well as the output for continuous time systems must be continuous time. Examples of continuous time systems include audio and video amplifiers, power supplies, etc. Right? Mathematically, it is represented as x of t produces y of t under the transformation h, or under the system h. Right, this is a continuous time system. X of t is a continuous time system. Y of t is also, x of t is a continuous time signal, and y of t is also a continuous time signal. The h is the transfer function of the continuous time system. We'll learn what is transfer function in the fourth unit, right? In the fourth unit, we'll learn what is transfer function and other stuff. So this is the block diagram or the representation of a system. So the driving function is the input. This is continuous time input, to the system with transfer function h, and finally we are getting a response y of t, which is also continuous time. So now the next one will be discrete time system. For the discrete time system, what will be the input and output? The input and output will be discrete time signals. It takes discrete time signals as input and produces discrete time signal as output. Examples of discrete time systems. Microprocessor is one example of a discrete time system. Microcontroller is one example of discrete time system. Shift registers are discrete time systems. Semiconductor memories like EEPROM, right? EEPROM, electrically erasable, programmable, read-only memory. This is also an example of a discrete time system. Mathematically, we represent discrete time system in this way. The input is a discrete time signal x of n. When it is fed to a system, discrete time system with transfer function h, it produces a discrete time signal y of n. So this is the representation of a discrete time system pictorially. Then generally continuous time systems are represented with the help of input-output differential equation. The output y of t and the input x of t are generally represented in terms of input-output differential equations. You see this d cube by dt cube. This is the differential equation, right? It consists of differentiation, so we call it differential equation. So this continuous time systems are generally represented with the help of input-output differential equations, right? So how do we find the order of such input-output differential equations? The highest derivative of the output signal. The highest derivative of the output signal is your order. Your output signal is y of t. So what is the highest derivative here for y of t? 3, right? 3 is the highest derivative for y of t. So the order of this system is 3. Similarly, so this is a third order continuous time system. Similarly for discrete time system. So for continuous time, we used differential equations to represent the input and output relations. For discrete time, we will not use differential equations. Instead, we will use difference equations to represent the input-output relations. So difference equations means it looks like this: y of n minus 2 or x of n minus 2. Those are difference equations. It is nothing but the delay. So how do we find order of such discrete time systems? The largest number of units of delay in the output signal. So whatever is the largest delay we have for the output signal y will be your order. Here y has the delay of 2, maximum delay of 2. So the order will be 2. If I write y of n is equals to y of n minus 3 plus x of n minus 4, right? X of n minus 4. So what will be the order of this difference equation? The output signal is y. Here there is no delay. Here there is a delay of 3. We are not concerned about the input signal. We are only concerned about the output signal. So the order will be 3, right? Then systems are systems are further classified into 6 different types. The first one is causal and non-causal. The second one will be linear and non-linear systems. Third one, time invariant systems and time variant systems. Fourth, stable and unstable systems. Fifth, static and dynamic. Static system or a dynamic system. Static system means it is also called memoryless system. Dynamic system means a memory system. And finally, invertible and non-invertible systems. First, we look at causal and non-causal. What is a causal system? A system is said to be causal if the present value of the output depends on present and or past values of the input. Whatever the time instant we have, see y of n here, y of n is equals to x of n plus 1 by 2 x of n minus 1, right? So the output at time n is dependent on input at time n and input at time n minus 1 So suppose let us say n is equals to 2. So the input at n equals to 2 and input at 2 minus 1 1. So the present value of the output signal, present value at 2 time instant 2, it is dependent on input at time instant 2 and input at time instant 1, that is present as well as past, right? So it is only dependent on present and past values. It is not dependent on future values. So therefore we call this as causal system. The system is said to be causal if the present value of the output y of n depends on the present or past values of the input. It must be dependent on x of n or x of n minus 1 or all the previous values. It should not be dependent on the future values, right? The next system, look at this: y of t is equal to x square of t. So at any given time instant t, the output y is dependent on the input at the same time instant, right? So if I take y of 0 is equals to x square of 0, right? If you want the output at time instant 0, you only need the input at time instant 0. If I take y of 4, it is dependent on x of 4 only, right? At time instant 4 only it is dependent. We don't need any other time instant, only the present time instant. So the system can be called as a causal system. Non-causal system. Non-causal system. A system is said to be non-causal if the present value of the output signal depends on future values of the input signal in addition to present past input values. So basically, if the system depends on the future values of the input in addition to present and past input values, or if it just depends on the future values also, we'll just call it a non-causal system. We'll just call it as non-causal system. So this is so if we look at this example, y of n is equal to x of n plus 1 plus 1 by 2 into x of n minus 1. So let us put n is equals to 0, y of 0 is equals to x of 0 plus 1, that is 1, plus 1 by 2 x of 1 minus 1, that is 0, right? So at any given time instant, at the time instant 0, the output depends on input at time instant 1, which is the future value, and input at time instant 0, which is the present value. It is dependent on both present as well as future. So we call that system as a non-causal system. This is the other example for non-causal system. So let me just substitute t is equals to 2. T is equals to 2. Y of 2 is equals to x of 2 square, which is 4. So at time instant 2, the output depends on the input at time instant 4, that is future value. So this is also a non-causal system. The next one is linear and non-linear system. The system is said to be linear if it satisfies the principle of superposition. If it does not satisfy the principle of superposition, we call that system as non-linear. To check the linearity of any given system, there are 3 steps we have to follow. Sorry, 2 steps we have to follow. First one is we'll consider a signal as a weighted sum of 2 input signals. So we'll consider 2 input signals, x1 and x2, and we'll consider a third signal which is a weighted sum of these 2 signals. So a weighted sum, that is, I'll multiply these 2 signals with with 2 coefficients and then I will add them, right? x3 of t is equal to a1 into x1 of t plus a2 into x2 of t. Then I will check my response of x3 of t, which is y3 of t. If I get y3 of t is equals to a1 into y1 of t plus a2 into y2 of t, then the system is called linear. If this relation does not hold good, if this relation does not hold good, then I call it non-linear system, right? This relation holds good, I call it linear system. This relation does not hold good, I call it non-linear system. Let us look at a few problems. So we were given a system y of t is equals to t into x of t, and we have to check if the system is linear or not, right? First, I can write this as y of t is equal to t into x of t, which is nothing but x of t is being transformed into y of t, right? So I'll write it as transformation of x of t. So basically I am giving x of t as an input to system H, and I am getting y of t as the output, right? That is, y of t is nothing but transformation h of x of t, the that is nothing but t into x of t, right? Now let us consider a signal x1 of t. Input signal x1 of t we will consider. Then what will be the response? We'll call the response as y1 of t. We'll call the response as y1 of t. So y1 of t is nothing but transformation of x1 of t, which is equal to t into x1 of t. Similarly, we'll consider another input signal x2 of t. The response of this signal will be y2 of t, which is equals to h of x2 of t, that is nothing but t into x2 of t. Now we'll consider the weighted sum of the two inputs, that is x3 of t is equals to a1 into x1 of t plus a2 into x2 of t, right? Weighted combination of both x1 and x2. So what will be the response? Response will be y3 of t is equal to transformation of x3 of t. In place of x3 of t, I am substituting a1 x1 plus a2 x2. So this is my input signal. This is my input signal. So what is happening to my input signal here, x of t? It is just getting multiplied by t, right? It is just getting multiplied by t. So whatever my input signal is there, I'll just multiply it with t. So t into my input signal. Now I will simplify this. a1 into t into x1 of t plus a2 into t into x2 of t. Now I'll take a1 and let me, what is this? What is this? And what is this? This is nothing but y1 of t. So a1 into y1 of t, and this is nothing but y2 of t. So a2 into y2 of t, right? So my y3 of t is equals to a1 y1 plus a2 y2 of t. This relation holds good. So what can we say? We can say the given system y of t is equal to t into x of t is linear. The given system is linear, right? First, we take an input signal x1 of t and find the corresponding response. Then x2 of t and its corresponding response. Then we take a weighted combination of these two signals and find the corresponding response. If the corresponding response is the same as a1 into y1 of t plus a2 into y2 of t, the given system is called a linear system. Now let us see another example, x square of t. So if I consider, so this is nothing but y of t is equals to x square of t. It is nothing but transformation of x of t, right? So let me consider an input signal x1 of t, x1 of t. Then my output signal y1 of t, or my response y1 of t, will be nothing but transformation of x1 of t, transformation of x1 of t, which is nothing but x1 square of t. So similarly for x2 of t, my y2 of t will be equals to x2 square of t, x2 square of t. Now I'll consider x3 of t as a1 x1 of t plus a2 x 2 of t. Now what will be my y3 of t? y3 of t will be x3 square of t, right? It must be equal to x3 square of t. That means x3 of t whole square, right? What is x3 of t? It is a1 x1 of t plus a2 x2 of t. So if I expand this, so a1 x1 of t plus a2 x2 of t whole square. So a plus b whole square formula. So what will it be? It will be a square, which means a1 square x1 square of t plus a2 square x2 square of t plus 2a1 a2 x1 of t x2 of t, right? So this equal to y1 of t plus y2 of t? Is that equal to y1 of t plus y2 of t? No, it is not equal to a1 into y1 of t plus a2 into y2 of t. It is not equal to a1 y1 of t plus a2 y2 of t. Hence, we call the system as non-linear. The system is non-linear. Okay, that is how we have to find linearity and non-linearity. So these are some other problems for your practice. You can practice these problems, and we'll move on to the next classification. The next classification is time variant and time invariant. A system H is said to be time invariant if a time delay or time advance of the input signal produces an identical time shift in the output signal. If you delay or advance the input signal, the corresponding output will also be delayed or advanced, right? Then the system is called time invariant. If x of t produces y of t, then x of t minus t should produce y of t minus t for all values of t. Then we call the system as time invariant. Otherwise, we call it time variant. Here we'll look at the procedure to check time variance and invariance. First, we have input x of t and its corresponding output y of t, right? So first what we'll do, we will delay the input signal by t naught. Delay the input signal by t naught, that is x of t minus t naught, and determine the system response for the delayed input signal. We will find the output or the system response for this signal. Next, we will delay the response of the system for original input. For the original input, what is the response? Y of t. We will delay y of t by t naught, right? Y of t by t naught. Here we will find the delayed response. This is the delayed response, and this is the response to delayed input. Let me just call it as R1, and y of t naught will be my R2, right? If both R1 and R2 are equal, then we call the system as time invariant. If step 1 and step 2 produce identical outputs, then we call the system as time invariant. Otherwise, we call the system as time variant. Okay, let us look at some problems. So this is the system given for us. We have to see if it is time variant or time invariant, right? Now, system responds to delayed input. Delayed input. System responds to delayed input. So the delayed input is x of t minus t naught, right? So wherever we have x of t, we'll just replace x of t with x of t minus t naught. That is how we will get the system response to delayed input. So what will be my system response to delayed input? It will be y of t is equals to t into x of t minus t naught plus 4, right? Now next we have to find the delayed system response. So that means we have to find y of t minus t naught. That means we have to find y of t minus t naught. That is, we will replace t with t naught. T with t naught. Sorry, t with t minus t naught. So this one, right? So if you look at the right hand side, here we have t into x of t minus t naught plus 4. Here we have t minus t naught into x of t minus t naught plus 4. Both of them are not equal. 2 is not equal to 3. Hence, the given system is time variant. If you look at another example, y of t is equal to e power x of t. Here, if you replace just x of t with t minus t naught, we get e power x into, e power x of t minus t naught. If you replace t by t minus t naught in the first equation, we get this. We get this equation. Both the equations are equal. They are similar, right? Hence, the given system is called time invariant system. It's very simple. The first one, we'll replace x of t with x of t minus t naught. In the second one, we'll replace t by t minus t naught. If both replacements result in the same response, then we'll call the system as time invariant. Otherwise, we'll call the system as time variant. These are the practice problems. You can check for time variance or time invariance. Next one is stable and unstable systems. A system is said to be bounded input, bounded output stable, BIBO stable. We call it BIBO stable. That is conditionally stable. It is conditionally stable. That is a bounded input, bounded output, right? If and only if every bounded input results in a bounded output. We can only say the output is bounded if the input is bounded. That is why we call it as BIBO stable, bounded input, bounded output. A system is said to be BIBO stable if and only if every bounded input results in a bounded output. Input, this is the input. We are saying it is less than infinity. It has some value and it is less than infinity. If that is the case, it has to produce an output of finite value less than infinite. That means this is bounded input and this is bounded output. So if bounded input produces a bounded output, every bounded input produces bounded output, then we call such system as BIBO stable. Otherwise, the system is unstable. Now, look at this system. Y of t is equal to a into x of t and a is greater than 1, right? I am assuming x of t is equal to unit step function. Unit step function, my x of t is unit step function, right? It is defined for positive values of t. This is my x of t, right? This is a bounded input, right? The value is never going to infinity anywhere. It is bounded. So y of t is equals to a into x of t. This is bounded. Is my a bounded is the question. If a is also bounded, then bounded input, this is bounded and this is bounded, so obviously my output will also be bounded. In the question it is given a is greater than 1, which means a can take the value of 10, it can take the value of 10 power 3, it can take value of 10 power 3000, it can go up to infinity, right? There is no limit on the value of a. So we will call this system as unstable because a can assume value of infinity, and when a assumes value of infinity, whatever your x is, whatever your value of x is, even if x is bounded, your output will always be unbounded. That means your given system is unstable, right? So if I say y of t is equals to, let me just check. Okay, y of t is equals to x of t into cos omega naught t, right? X of t into cos omega naught t. This is my system. This is another example. Let me consider my system y of t as x of t into cos omega naught t. Now we need to see if this is stable or unstable. So again I'll consider x of t as u of t, right? Which means x of t is bounded, right? So let me take modulus of y of t. Modulus of y of t. What will this be equal to? It is equal to mod of x of t cos omega naught t, which is less than or equal to mod of x of t and multiplied with mod of cos omega naught t, right? What is the maximum value of cos omega naught t or cosine function? Maximum value will be plus 1. It varies between plus 1 and minus 1, right? So modulus of this will be equal to 1, right? And I'll get modulus of x of t here, right? So it is less than or equal to x of t, mod x of t, right? So my mod y of t is less than or equal to mod x of t. So if my input is bounded, I'll assume x of t is bounded. That means it has some value which is less than infinity. Then y of t must be less than or equal to that value, right? Y of t is less than or equal to that value, which means y of t is also bounded. For a bounded input, I am getting a bounded output. Suppose let me say my x of t is 10. My y of t value must be less than or equal to 10. So it must be some bounded value, not infinity, right? So the bounded input is creating a bounded output. Bounded input is producing a bounded output. Hence, this given system is a stable system, right? These problems are for stability. You can use these problems as examples for stability or unstable systems, stable or unstable systems. Next one is static and dynamic systems. Static system means memory-less system. Dynamic system means memory system, right? Static system has no storage devices and the output signal depends on present values of the input signal only. It depends only on the present values of input signal. It does not depend on past or future, only at the present, only on the present. It has no storage devices. It can't storage past values. It can't store future values. So it does not have any memory. Hence, a static system is a system whose output signal depends only on present values of the input, right? Dynamic system is it has memory. That means if the output signal depends on either past or future, then the given system is called dynamic system. It has storage devices, right? If you look at the static system, resistor is a static system. It has no storage. But inductor or capacitor, they are storage elements. They can be considered as dynamic systems. This system here, at given instant of time, at any instant of time, the output is dependent on present, also past inputs. It is dependent on past. That means it has some memory. It is remembering what is the past input and using that for present output. So the system is called dynamic system. This system here, it has resistance which has no memory, but here there is a capacitor is a storage element, hence it is a dynamic system or memory system. The next one, the last classification will be invertible or inverse systems. Invertible and inverse systems. If a system is invertible, it has an inverse system. There should be one-to-one mapping between input and output at every instant of time, right? If at every instant of time, if there is one-to-one mapping between input and output, then it is possible to get the inverse of the system. If you look at this example, y of t is equal to 2 into x of t, right? Let me take x of t and y of t. If x of t is 0, my y of t will be 0. If x of t is 1, y of t will be 2. If x of t is 2, y of t will be 4. If x of t is minus 1, y of t will be minus 2. So if you look, there's only one-to-one mapping. No two values of x of t, no two values of x of t is giving the same output of y of t, right? There is one-to-one mapping. That means if y of t is 0, it must mean by x of t is 0. X of t can't be any other value, right? So it is invertible. We can get x of t from y of t as well. That means there exists an inverse system. So the system is invertible. That means for any x of t, we get a distinct output y of t. Hence, the system is invertible. Suppose if I consider x of t or y of t is equals to x square of t, right? So let me just consider x of t and y of t. For minus 1, I'll get 1. For 0, I'll get 0. For 1, I'll get 1. For 2, I'll get 4. For minus 2 also, I'll get the same 4, right? This is many to one mapping, right? This is many to one mapping. Two different x of t is giving me the same y of t. So if I have y of t as 1, I am not sure if my x of t is minus 1 or plus 1. It can be either one. So it is not a invertible system. So if there is a many to one mapping, the given system is non-invertible. If it is a one to one mapping, the given system is invertible. So that is the End of classification of systems.